Alright, so now that I have explained to you the mode 1 optimum, if I try and increase the throughput to maximize the throughput, which is mode 2, what happens is, in addition to those 3 constraints, V3 max also goes active. The boil up on the product column goes active, and that limits my throughput. And of course, these 4 variables remain economically important, because again I want to make sure that my reactor operating conditions are such that conversion is high and selectivity is not too low. Well, that is that. The rest of the stuff is as in mode 1. So, it turns out that V3 max is my bottleneck constraint. This is the constraint that limits my throughput, maximum boil up in the third column. Okay. Now, just to contrast, let us put up a control system. The conventional approach is, this is C3, the conventional approach is, you basically choose your throughput manipulator at one of the process feeds and then put in your total material balance loops and then the other loops. Okay. So, what do I do there? Since the limiting reactant is C3, I use that as my throughput manipulator. Okay. Then what I need to do is control the level. So, if I want to control the level of the vaporizer, well, the level has to go this way. Okay. Then I need to control what? Let us put in all other total material balance control loops. So, this one is needed to condense. So, I will put a temperature controller this way. Then I need to control the level of this chap. How do I control? Oh man, that valve is quite far away. So, let us just say this valve is not here, let us just say this valve is here, right here. So, what do I get? I basically get a level controller this way, and I get a level controller for the top this way, I get a temperature controller this way, and I get a, this is the material balance control on the column, vapor and liquid. Then on this column I get level control this way, on this column I get level control this way, pressure control this way. Okay. And then I get my pressure controllers and level controllers as before, okay, and level control this way. Okay. Now, what do I do with this chap? Yeah, the conventional thing to do. Why did I put in the furnace there? It was put to control the temperature of the reactor feed. So, that is what I do using this. Of course, what do I do with this valve? Of course, I shall set the cooling rate such that temperature of the shell is maintained constant at whatever was its near optimum value over the entire throughput range, which was I think 367 degrees Celsius or something like that. Okay. Then what do I use this valve for? Well, this valve will be used for keeping the pressure of the reaction section. Okay. How many valves are left now? I am left with this valve, that valve, 1, 2, 3, 4, 5. I am left with 5 valves. Okay. The total benzene flow reflects the inventory of the benzene, and therefore, I do a total benzene flow control inside the process, and this makes sure that I do not put in too much benzene or too little benzene. I put exactly the amount of benzene that is required in order to eat up the C3 that is being fed. Okay. So, I have taken care of that. Now, let us start doing some stuff. I am going to set the reflux in ratio with the feed to the column. Okay. So, I take the reflux, the feed, I multiply it by the set point, and this is going to set the reflux into the column. This is a set. Okay. Then I need to control the, of course, the inventory of propylene dropping down is controlled by doing this. I also, but you see, okay, on this column maybe I should change the colors, because on this column what do? I say, well, boil up needs to be max, okay. So, if but I do not really have not done the optimization. So, conventionally what I would do is I will control a tray temperature and there will be a V1 max or V2, this is second column. So, V2 max, and of course, between these two the low select is what will manipulate the steam. Oh well, there is also just a second, because it is just to be consistent, it is actually setting the boil up. Okay. Similarly, on the second column, on the product column, which is the third column, I have a similar arrangement. Temperature controller goes to a low select, V3 max, and then I have a boil up controller, and the low select output is setting the boil up. Okay. Then which valve is left? Yeah, I have got this valve that is left. What do I use it for? Of course, I have to use it for product purity control, and therefore, what I basically say is I am going to do this composition control. Which composition? C12, by adjusting the reflux. This is what I would do conventionally. Of course, I would also have another composition loop, because I have C6 as another impurity here. So, this will be C6. This composition loop will set the set point of the temperature controller. So, oh, just a sec. So, yeah, this guy is setting this chap. Now that I have done this, my control system is complete. Now, let us say I am increasing throughput. Okay. Strictly speaking, I want to operate the process even in mode 1 at as high a boil up as possible in the recycle column. So, I want V2 max, I want the temperature to be controlled, because if the temperature goes uncontrolled, what that will mean is that too much benzene can leak out and contaminate my product. I cannot afford to lose benzene product impurity control. So, therefore, this temperature controller on the recycle column has to be always on. Okay. What that means is I cannot have V2 max ever going active, because if it goes active, then I am in trouble. I am losing benzene impurity control. Okay. What about this chap, the temperature controller on the third column? Well, again I cannot afford this temperature control to be lost, because if it is lost, then too much cumene will leak out the bottoms, and cumene is precious, that represents a significant economic loss. Okay. So, now how do I manage it? I say that, well, in order to keep V2 at max, because that is what I want to do, now I am putting the optimal constraint controllers. Since V2 is to be max all the time or close to max all the time, what I will do is I will adjust, I put a supervisory controller that takes the boil up, do a valve positioning controller which basically sets the total benzene, and its set point will be V2 max minus delta. It will not be V2 max, but slightly below V2 max, so that should there be transients that cause the temperature in the column to deviate, it should not happen that I lose the temperature control because V2 max got active. Okay. So, I will have to have some amount of back off to make sure that V2 max never goes active, regardless of the worst case transient that this process has to deal with. Okay. So, the first disadvantage is in this control system you have to have back off in V2 max. Now, as I am jacking up the throughput, that means the operator is increasing the C3 set point, he does not know when to stop. What happens is V3 max goes active. Once V3 max goes active, either I put in a loop that goes from here to here, that will be a very long loop, okay, or I alter the material balance control structure, which is what I do. How do I alter the material balance control structure? I am going to put that control system here. Okay. So, there will be a low select here, there will be an override temperature controller, because I cannot afford to lose, and of course set point 2 and this is set point 1. I will have, like I discussed earlier, set point 2 must be less than set point 1. Okay. Now, when level control is lost, I need an alternative handle, and that is what I do here. Again I have a low select, and I have an override level controller. How should I draw it? Okay, so there is an override level controller whose output is going to this chap, and these are inputs, this is the output. Okay. And once this override level controller is lost, well, what I do is, what I do is over here I also have a low select. What that does is override level controller, that basically, and this is the operator input set point, flow set point, flow of the propylene set point. Okay. Now that I have drawn it, let me just explain it. See, the set point of this override level control, okay, OLC set point is greater than LC set point, corresponding nominal level controller set point. So, the override level set point is greater than the nominal level controller set point, the same level. Okay. Now, let us see how things go. At low throughputs, V3 is not active. So, because V3 is not active, temperature control is using boil up. Why is temperature control using boil up? Because the override temperature controller set point is less than the set point of the nominal controller, and what that basically does is that the override temperature controller sees that, look, my temperature of the tray is actually higher. So, if the temperature is higher, I need to put in more feed to get the temperature back, and therefore, the output of this controller is actually high. Because the output of this controller is high, the level control, level control of, basically this signal gets passed. So, the feed to the product column is under level control of the recycle column, bottom of the recycle column, and so on and so forth. Now, let us say I am increasing this set point. As I am increasing this set point, what will happen is V3 max will become active. When V3 max becomes active, temperature control will be lost of the stripping tray. This temperature will then, because temperature controller is saying increase the boil up, but V3 max has gone active, boil up cannot be increased, therefore, temperature will start to go down. As temperature starts to go down, it will go below the set point of the override temperature controller. Now, the override temperature controller will say, oops, my tray temperature is lower, that means I am putting too much feed. So, this output of the override temperature controller will start to go down. Ultimately, it will go below the level controller set point, and therefore, my control will pass from the level controller to the override temperature controller. So, the feed to the column, to the product column will now be under override temperature control. Okay. Now the level is uncontrolled on the recycle column bottoms. So since this level is uncontrolled and I am putting in too much feed, what will happen is the level of this column, the level of this bottoms, the bottom sump will start to go up. As this level is going up, what will happen is this level will go beyond the set point of this override level controller. As it goes beyond the set point of this override level controller, the override level controller will say, oops, my level has increased too much, I need to reduce the feed, and because the override level controller output is now decreasing, it will ultimately go below, it will ultimately go small enough so that the low select selects it, and therefore what will happen is the feed to the recycle column will now be controlling the level of the bottoms of that recycle column. And now what will happen is the level on the purge column bottom will be uncontrolled, therefore this level will start to rise, and ultimately this level will rise so much that the override level controller on the purge sump column on the purge sump, that override level controller will say, oops, my level has risen too much, reduce the propylene feed, and ultimately this low select will pass the level controller set point to the propylene feed flow controller. And therefore what happens is once V3 max goes active, I basically alter my material balance control structure from V3 max all the way up to the propylene feed. Yeah, this is what I do. Okay, what is the disadvantage? A, please note that you need 3 override controllers. Okay. Also please note that because SP2 is less than SP1, you will actually have more leakage of precious cumene down the bottoms, that will happen. Yeah, that is just to make it work. Okay. And the further the difference, the more the leakage of precious cumene down the bottoms. So you will have more loss of precious raw material. Also notice that in this scheme, the other constraint which was V2 max, you will have to operate at some amount of back off. This back off is delta, and therefore what this means is in this control system you get greater cumene loss in the DIPB byproduct stream, as well as the process will operate on average at a slightly lower V2 at a boil up that is slightly lower than V2 max, which basically means that the selectivity will be slightly lower. So the selectivity will be slightly lower, and also cumene loss will be slightly greater. Okay. Now let us contrast it with our approach of doing things. How do we do things? Well, what we say is V2, let us look at the maximum throughput constraints. All constraints that are active at maximum throughput need to be tightly controlled. Okay. If that is what I want to do, what I will do is I will basically put in a loop that does this, I will put in a loop that does this, and I will say this set point, because this control is going to be very tight, this set point can be set at V2 max without any back off or negligible back off. This will be V1 max. Okay. Then what was the other constraint that was active? Yeah, the other constraint active was P reactor max. Okay, so this is going to be pressure. This is the same as before. So here I get, because I want to operate the reactor at maximum pressure. Also I have this loop because composition control of C12 is by adjusting reflux, and this will be a nice and tight loop. Okay. And this is being okay. Let us see also. So these loops I have put in place just based on constraints at maximum throughput. What are the other economically important things? The other economically important things are, I want temperature to be as small here as possible so that I get minimum benzene loss, that's as before. I also want the temperature, tight control of the temperature into the reactor, because the reactor is quite exothermic. Okay, so that will do that. I also set this temperature is equal to 367 degrees Celsius, so that yeah, so this is also set at its optimum value, T optimum, whatever it was, I think it was 330 degrees Celsius or something. So the reactor inlet and the reactor shell temperature are set at appropriate values that ensure that the conversion and selectivity are maintained. Okay. Now that I have done that, what else will I do? Let's see. Yeah, I need to tightly control the benzene leaking down the bottom. So to do that, I put in it. Okay, economically important things. You see, I want tight control of this chap. However, boil up is max. Because boil up is maxed, this temperature cannot be controlled using boil up. So what are the options that I have? I can control it either using the feed or the reflux. Since the feed is closer, it will have a faster impact. So what do? I control temperature this way. I also need tight temperature control of the benzene leaking down the bottoms of the recycle column of this column. However, its boil up is also at maximum, so therefore I cannot manipulate the boil up. So what do? Similar logic, I control temperature using the feed to this column, and of course I have a benzene composition controller, composition of C6, and that composition controller is essentially setting this set point. Yeah, so this is setting that set point. Sorry, set. Okay, so that takes care of economically important things. What else? Of course, I want to make sure that too much C3 does not leak down the bottoms. That gets done using this. Okay, what else? I also need to make sure that whatever are the condensables in the reactor effluent, they are condensed. This ensures that. What else? I need to ensure that the reflux in the recycle column is high enough so that not too much cumene leaks up the top of the recycle column. So what do? As I was doing before, I do it the same way. Okay. Anything else? So this takes care of most of the all the economically important things that have a steady state effect. I have put in the loops. Now let me put in the material balance control structure. So for material balance control, I need to have pressure control. Pressure control on all the columns will be basically conventional. So I got pressure control, and I've got same thing, pressure control. Okay, now how about level controllers? Well, this is conventional level control. This is also, well, how do I put it? Just put a level controller here, and it is conventional. How about level control of this chap? Well, I have got level control this way. What about level control of this chap? Well, I got level control this way, local pairing. Okay. Now, I have a problem in the sense that, what about this level? You will notice that I have basically used up all valves that are local to this column. What about the level of this chap? You will again notice that there are, oh well, I forgot a loop, oh just a sec. So of course there is level control here this way. So once I have put all these things in place, what I find is that the levels in brown, there are no close by valves that are available to control those levels. Okay. So how do I control this level and how do I control this level? I can see that the only valves that I have available are actually the two feeds, the C6 feed and the C3 feed, C3, C6. Okay. So what do? Let us see if it makes sense. Let us say I control the, what does this level represent on the recycle column? This level actually represents C6, C9 and C12, which are separated downstream, yeah, in the product column. C9 and C12 are essentially reaction products, and if this level is increasing, what that means is that I am producing too much C9, C12 in the reactor, which is accumulating in this column bottom. Okay. So, what that means is I need to reduce the ethylene to reduce the amount of C9 and C12 formed in the reactor, so that this level may go back. Yeah, that makes sense. What about this level? Well, this level is because benzene is in large excess in the column. So, this is what accumulates here is a lot of C6, C9 and C12, but C6 will be the dominant component. So, what I can actually do is I can control this level using a C6, and I can control this level using this chap. Yeah, you can see these level loops are long. Contrast this with what we did previously. You see, here I have a long economic loop. This is a long loop for V1 max, for ensuring V2 max. Column 2 is operated close to V2 max, and I also have a long override scheme that alters, you know, from here to here to here, well, to here. I have a long override scheme that alters the control structure when V3 max goes active. Okay, contrast this with this chap. Did it go? Yeah. Here I am having V1 at V1 max, no back off, V2 at V2 max, no back off, but what I have are long level loops, two long level loops. So, there were two economic constraints. In the previous case, what I had was one of the economic constraints, which is, oh sorry, this is V3 max. One of the economic constraints, which was V3 max, that was controlled using overrides, and the other economic constraint, which was V2 max, well, you had to have back off there. Okay. And why did you have to have back off there? Because this loop out here was a long one. So, you had a long economic loop and local level loops. In this case, what do we have? We have local economic loops and long level loops. So, I have got long level loops and local economic loops. This is a long loop, this is a long loop. So, that is the difference in these two approaches. Now, the question is, will these level controllers work in practice? Well, it turns out that what do you have in this column? You have a small amount of lag in the vaporizer, which is small, and then you essentially have flow through a pipe, because everything is flow through a pipe. So, there is a small lag associated with this chap, there is a small lag associated with the condenser, but the rest of it is just flow through a pipe. So, really speaking, when I change the benzene, when this level controller changes the benzene, its effect will reach the bottom actually in, let us say, 5 or 10 minutes. Since my sump is having a residence time of 5 or 10 minutes, this level control should work reasonably well. Similarly, the same logic also holds for this chap. Okay. And it turns out that we did the simulations, and it did turn out that for the disturbances that we considered, which were pretty large, you are able to operate the process with these levels fluctuating in a larger band, but not hitting high level or low level alarm limits. So, in this control system, what I have done is essentially transform the variability to the levels. Levels do not affect my economic steady state. Since levels do not affect my economic steady state, I would like to transform my variability as much as possible to the surge levels. This is a surge level, this is a surge level, and that is what this control system is doing. Okay. So, I hope this example actually brings out the difference in the two approaches. Okay. So, the trade off is basically this: you could have local level loops, and long constraint control loops. What should I say? Active constraint control loops. Active constraint control loops. This is the conventional approach. In our approach, what we do is, what we are basically doing in our approach is long level loops instead of local level loops, and we get local active constraint control loops instead of long active constraint control loops. So, because active constraints, back off from an active constraints affects my economics significantly, this gives me significant economic advantage. Alright. Now let us see, okay, just to complete this case study, what do I want to say? I want to say, okay, if you are, let us say you want to reduce the throughput. See, this control system will work at maximum throughput. If I want to reduce the throughput, what do? I basically say, well, low select V3 max, and of course, the operator inputs a V3 set point. So, when V3 set point is less than the flooding limit of this column, so if I reduce this set point below V3 max, you see the boil up will reduce. If the boil up reduces, temperature will reduce. If the temperature reduces, the temperature controller here will reduce the feed. If this feed if this flow reduces, the level here will actually start to go up. If the level if the level here starts to go up, this level controller will basically reduce the propylene. Yeah, so this is how throughput will reduce. Okay. So, it is a very simple scheme, no alteration of the material balance control structure depending on which constraint is active and which constraint is not active. Regardless of where you are operating, regardless of what throughput you are at, the basic inventory management scheme remains the same. Okay. So that is that. I think this case study actually sort of brings out the contrast between the conventional pairing approach and the actual pairing approach and the economic plant wide control approach that we are proposing. Okay, so I think that takes care of that. With that, we have got still some time, so let us see. Maybe we can do another case study, but I will leave, we have done enough number of case studies. Maybe what I want to do is basically summarize what we have done in this course, and then let's just leave it at that. So, before I end, I just wanted to add one tidbit on override controls. See, so let us say I have got a low select, okay, and let us say there are two controllers. I do not want to say what controllers they are, and let us say they are moving a valve. This is a general arrangement, okay, and there is, what should I call it? Let us say there is a PI controller number 1 and there is PI controller number 2, which is controlling something. It is not really relevant what you are controlling, but as long as it is clear to us that this valve is being adjusted to maintain either this or that, and that depends basically on which signal is greater of the two. Now, and both of these controllers are PI. If both of these controllers are PI, let us say what we have is, we have the operating condition is such that this valve is under control of this chap. Then what happens is, this guy is off. So, whatever it is trying to control, it will move away, and by design what will happen is, in order to get its control back, what this guy will say is, oh, its output will keep on increasing. Okay. Because its output will keep on increasing, let us say this output goes and saturates at 100%. Let us say this output is at maybe 50%. So, what happened was, when this output increased above 50%, control passed to this chap, and now because control has passed to this chap and this chap, which is this chap, is uncontrolled. To get control back, what this guy is saying is, well, move the valve, and the movement of the valve will actually be in the direction that takes this away from this. Okay. Now let us say the operating condition changes, and now control has to pass from this guy, from this guy to this guy. So control has to pass from this guy to that guy. Now what happens is, this output is at 100%. The integral action in this controller actually caused this output to reach its saturation limit. Now what has to happen is that this controller has to unwind from 100% to 15% to 50% before control passes from here to here. So there will be a very long period where control did not pass from here to here. Okay. Shinsky has proposed what is called an external reset wind-up scheme, and in the external reset wind-up scheme, just to explain that, what I wanted to just to explain that, let us see what external reset actually means. Okay. If you look at a PI controller, you have the error signal that comes, you multiply it by Kc, and then there is a bias term that you add, a bias term, let us just call it B, and this is the, so U, this is the, so U is equal to Kc times E plus a bias term. Okay. Now let us say I put in an integrator with a certain gain associated with it. Let us just say I put 1 by tau I, okay, and I try and make sure that the bias matches the output of the controller. So this is the bias and this is the output of the controller. So, well, yeah. Okay. Now if I look at this guy is actually B is equal to, by block diagrams, 1 by tau is whatever is in the forward path divided by 1 upon 1 by whatever is in the forward path divided by 1 plus whatever is in the forward path, that is. So B by U is equal to this chap. Okay, and if I solve this, this will come out to be actually 1 over tau is plus 1. So what this means is, this chap over here that is trying to make sure that the bias is adjusted to match the U, this chap can actually be replaced by simply a lag, a simple lag, yeah, and this lag is actually this chap, lag of gain 1 and time constant tau I. Okay. Now at final steady state, what will happen? At final steady state, because this is just a lag, B will be actually be equal to U. If B is actual to U, what must this signal be? This signal is actually KCE, KC is non-zero. If KC is non-zero, this guy at final steady state, this guy must be 0. Unless this guy is 0, B cannot match U. So this is another way of looking at PI controller. A PI controller may also be looked at in this way, where you are adjusting the bias so that it matches the controller output. Okay. So this is again a PI controller, and just to convince you it is actually a PI controller, let me just show you. So what is U? U is equal to Kc times E plus B, and B is equal to U times the lag, and the lag is 1 by tau is plus 1 times u. If I collect the terms of u on one side, what I will get is u times 1 minus 1 by tau is plus 1 is equal to Kc times E, and this will give essentially tau is plus 1 minus 1. So, 1 and 1 will cancel out. So, what I will get here is tau is over tau is plus 1, and then what I will get is u is equal to Kce times tau is plus 1 divided by tau is, and then what I will get is u is equal to Kc times E plus 1 by tau is of E. This is the PI controller transfer function. This is nothing but a PI controller. So, you can see that this block diagram that I have drawn is actually nothing but a PI controller. Okay. Now, in terms of overrides, the thing that I was talking about, when I am doing my overrides, and let us say I get back to the same thing as before, let us say what I have is two controllers competing for control of a valve, two PI controllers. So, I have PI controller number 1 and I have PI controller number 2, and both of these, let us say, are competing through a low select or a high select. These are the two outputs, and this is basically going to a valve. Okay. The block diagram that I just drew, the reset action B is taken from the implemented controller output u, B is equal to a lag times u, that is what I was doing. This is actually called, Shinsky calls it external reset. Now, when two PI controllers are competing for the same valve, instead of taking your reset action from here and from here, so basically this PI controller will actually be some Kc, some K2 times error in the second variable, and I have a lag which gets added here. Similarly, this PI controller can be seen as, you got the error in the second variable, you multiply it by in the first variable, sorry, you multiply it by a gain, and then add to it lag 1, and let us just call this lag 2. Okay. These are the two controllers that I have. Okay. So, this is PI 1, oh sorry, this is PI controller 2, this is same thing PI controller 1. Well, if I take this external reset from whatever is implemented, you see this is the signal that is getting implemented. If I take external reset from whatever is implemented, then please note that this bias and this bias will keep getting updated, to match, the bias will keep getting updated, so that the implemented signal, the bias B2 will get updated so that B2 is close to u. Similarly, B1 will get updated so that B1 is close to u. So, when let us say this guy is inactive, if this guy is inactive, if this chap is inactive, that means this signal is getting passed, this signal is actually passing through. So, if this chap is inactive, the second controller is inactive, then what will happen is, even though control this signal is getting passed, this bias B2 will keep getting updated so that it matches U. What that means is this signal will differ from this signal only by whatever is the error here, and if this error remains small, that means the deviation error does not change by much, then what that means is this guy will not go too far away from that guy, and the problem that I was talking about, that this controller must unwind from 100% to the value here, that must happen, that need not happen, because now the passing over of the control is based purely on proportional action, not on the integral action. Okay. So, this is actually a very neat trick. This is called external reset by Shinsky. Shinsky calls it, by the way, Shinsky probably got everything right. Shinsky calls it external reset, and he came up with very simple solutions for problems that you would face, for practical problems that you would face. External reset. So, when you take the reset from the control signal that is implemented, then you will make sure that if this is U1 and this is U2, then you basically make sure that U1 minus U2 is essentially of the order of k times E of whichever this k is of whichever controller is inactive, whichever is inactive, of the inactive controller. And if this E does not grow too much, the difference between what is implemented and what is not implemented will not be too large, and then this reset wind up problem that basically requires controller to unwind substantially the controller, because the controller outputs are substantially far away, that problem does not occur. Okay. This is the one thing that I wanted to tell you about override. So wherever a PI controller is competing for a valve, its reset action must be taken as an external reset of the signal that gets implemented, regardless of whether the controller is active or inactive. Okay. This was the one thing that I wanted to tell you, and I think with that it is time to summarize what we have done. In summary, all I want to say is, without getting too mathematical, what we have covered are essential process control fundamentals, essential process control, that is it, things that are of use in practice, not too much of theory this way, that way, advanced process control, etc., but essentials. Then we looked at degrees of freedom, okay, and came up with a very intuitive way of figuring out what the degree of freedom of a process is. Then we looked at control of ordinary unit operations, control of unit ops. Finally, we looked at plant-wide control, and what I have tried to show you is that there is a conventional approach. In the conventional approach, and then there is the economic approach with constraints. And it is in this economic approach that you pair loops first for what is economically important and then do the material balance control, and I hope that all of this sort of convinces you that, look, designing a plant-wide control system is like piecing a puzzle together. How you piece the puzzle together, what approach you take to piece that puzzle together. One approach is the conventional approach, the other approach is the economic approach. Okay. That is where the, what should I say, that is where the art is, that is where all the confusion is, and I hope after going through this course at least some of the confusion will get clarified. Okay. I think that is a good place to end this course. Thank you.